Hello, and welcome to the June webinar presentation by the Underground Construction Association Younger Members Group. My name is Colin Sessions, and I am one of the members of the UCA of SME Standing Committee for Younger Members. I am joined by Anthony Bauer, the Chair, Shannon Goff, the University Outreach Chair, Everett Litton, the Membership Chair, Demetrio Cuscolo, and the Media Chair. The UCA Youngers Members is a standing committee of the UCA of SME. The Younger Members Group is a group of professionals of all ages who strive to attract and develop engineers and construction professionals under the age of 35. Each month, we put on a free webinar on tunneling topics available to all interested parties. This month, Dr. Bedi will be presenting on the Victoria Station Upgrade Project. Dr. Bedi is currently the Managing Director of Bedi Consulting and is a chartered engineer with over 14 years' experience in the design and construction of tunnels and underground structures in both soft and fractured rock masses. His expertise includes detailed design and construction of tunnels using both native methods and TBMs, the detailed design and construction delivery of large and complex urban stations, and NATM drives adjacent to existing operational platform tunnels in shallow urban environments. Dr. Bedi has been employed as a specialist consultant for design of numerous complex tunneling projects in both urban environments, including Crossrail, C-121, Bond Street Station, and Victoria Station Upgrade, amongst others. Dr. Bedi, thank you for presenting to us today, and when you're ready, please share your screen.
Okay, thanks again, everybody. As I said, I'm Anmol Bedi. I'm a consulting engineer in London, UK. This morning for you, we've got a case study on Victoria Station Upgrade, which is a station upgrade in the centre of London that I've been involved with during detailed design and construction for the past 9 years. Let's move forward. Just a little bit about Victoria Station Upgrade. It was the client there was London Underground Limited, who runs the subway, with the principal contractor, a joint venture between Taylor Woodrow and BAM Nuttall. Mott MacDonald were the principal designers, to whom I was a subconsultant, and Keller were the ground treatment subcontractor. In today's presentation, I'll start with an overview of the project, just so you can familiarise yourself with the surroundings in the area. But what I'd like to particularly focus on is the technical aspects of Victoria Station Upgrade. So I'll be looking at introducing the challenges that we faced at VSU and what made it a unique project, and the solutions that the design and construction team developed to overcome these challenges and successfully deliver the project, followed by a quick wrap-up on proceedings. So starting with the project overview, this is a screenshot. So the picture shows an aerial view of Victoria Station. If you can see my mouse pointer, where I'm pointing now is the Victoria train terminus. It's one of the busiest train terminuses in London, indeed the UK. We have a bus terminus next to the train terminus, and urban environment overhead. So Victoria Station Upgrade is tunnelled directly beneath these buildings, linking the train terminus to the underground complex below ground. The reason Victoria Station Upgrade was conceived and constructed was that currently the station is subject to a massive amount of overcrowding and congestion. The station itself actually handles more people than Heathrow Airport, and something like 40 million people per year. And as you can see by the pictures on the left, it actually creates quite unsafe conditions with severe platform overcrowding. Trains at Victoria or underground subway run every 1 3/4 to 2 minutes. So this is the current layout. Sorry, not the current, as we've now finished construction. This is the layout of Victoria Station Upgrade prior to the upgrade works. So in blue we have the existing northbound and southbound London Underground platform tunnels at a lower level, and at an upper level you can see in green is the District and Circle line, which was constructed in the late 1800s. It's brick construction and it's quite shallow. The problem with the station, as you can see, is that it's single-ended. So where my mouse pointer is at the moment is the only bank of escalators and the only means of entry into the Victoria line and interchange between the Victoria line and District and Circle line, hence causing overcrowding. The Victoria Station project upgrades is a series of platform tunnels, paid area link tunnels, which we call PAL tunnels, which are shown in grey, and two new ticket halls, one at the south, where my mouse pointer is now, and one at the north, where I've now moved the mouse pointer to. And essentially, it would enlarge the station capacity by 133%, create a new escalator bank at the north end, where I'm pointing the mouse now, and essentially ease congestion. So you can see the proposed tunnels are quite intertwined amongst existing infrastructure. So that was one of the challenges. The other challenges were that London Underground wanted to keep the station open and operating at full capacity during the works. So one of their key objectives was to minimise disruption and develop efficient and program compatible solutions that would comply with their existing standards. To minimise disruption, you can see one of the primary challenges was keeping Victoria moving. So going back to the aerial photograph here, now we've got the start of enabling works at Victoria, and you can see the site hoardings running along the lines. Numerous traffic diversions were required to undertake the works. Where my mouse pointer is at the bottom of the screen now, you can see the Grade 2 star listed Victoria Palace Theatre building, which we tunnelled beneath, and I'll go into some more detail later. So before starting any of the tunnelling works, just the enabling works presented an immense challenge in itself. The contractor, Taylor Woodrow Van Nuttall, had similar design expectations, requiring minimal operation, simplicity, ease of logistics, and reduction in risk during the tunnelling activities. In terms of the technical challenges, one of the key challenges of Victoria is the extreme geotechnical hazards. You can see here on the picture on the right where we've got the tunnel portal. The tunnel's excavated at a very shallow depths. Where my mouse pointer is now, you can see the start of the tunnel portal. That's an 8.5 metre diameter tunnel with only about 3 to 4 metres of cover to the surface. You can see just beyond the hoardings where I'm pointing to now, the bus terminus, so buses passing overhead directly above the tunnelling works. You can see the buildings and Victoria Palace Theatre in the background on the surface level. The primary challenge at Victoria, however, was the ground conditions. So the tunnels, where you can see my mouse pointer now, that form Victoria Station upgrade, were constructed in a mixed face of water-bearing river terrace deposits and London clay. I'm just going to have to take off the slideshow here, and I can show you what the ground conditions. I have a video of the ground conditions. This is essentially what we were dealing with. So this is a hole about the size of a football in a pile excavation near Victoria, and we can see the water-bearing ground essentially flowing. So there we have it. That was the ground that we were dealing with essentially. Here's a cross-section through one of the escalators that shows the challenge of constructing Victoria through such ground and shallow overburden. You can see here an escalator diving down from ticket hall level down into the clay beneath the water-bearing river terrace deposits, which are up in the crown. So as you saw, any inrush would be catastrophic, and this was essentially leading into the Victoria Station. You can also see here the foundations of the Victoria Palace Theatre, which is the Grade 2 listed building, within metres of the extrados of the excavation. So essentially we're working in a very confined environment, both in terms of adjacent underground assets and above ground assets, coupled with the geotechnical conditions. It's an isometric view of that same escalator diving down. And again, going back to the expectations of the client, London Underground and the contractor, we were tasked with keeping the platform tunnels operational with trains running at peak hour every 2 minutes. So you can see the isometric here and the platform tunnels depicted in blue, and passenger tunnels in dark blue through the centre. So all these remained operational throughout the extent of the works, obviously posing very unique and very challenging technical conditions. Right, so our solutions to these challenges, which is the main part of the presentation. Here we've got a visualization of the ground conditions. Essentially, we've got one of the paid area link tunnels you can see here. So up the top, we've got a few metres of made ground, which is essentially fill from the construction of London, comprising all manner of fill. Below that, we've got a thin layer of alluvium. Followed below this is the river terrace deposits, or the terrace gravels, which have about 1 metre and 1.5 metres of dry conditions above the water table. However, we then encounter the water table and the river terrace deposits below about shoulder level of the tunnels. And as you saw from the video earlier on, any breach of ground would cause a major inrush and essentially collapse to the surface. To overcome this, during the design phase, we had a look at the options of stabilising that ground. This is a picture of how Victoria Station was built in the 1960s. So the previous excavation was open face, using chemical ground treatment, in this case permeation grouting. However, where you can see highlighted on the picture on the right in red and in blue, during the 1960s and subsequent passenger relief works in 1992, using permeation grouting, we had a series of collapses in the area. So there was obviously a lot of perception of risk prior to the start of the project and whether or not the ground treatment would be successful, and we would be able to tunnel Victoria Station upgrade successfully. In terms of the ground treatment options, we had a look at various ground treatment options, obviously reviewing the risks from past projects in the 1960s and the 1992. And what we came up with was a solution where we required a completely tanked environment in which we could undertake the tunnelling, and this was in the form of a 2-metre annulus. And you can see here we've got the ground conditions with the groundwater table at the indicated level, the extent of the tunnels. And what you can see here is, in yellow, the extent of ground treatment that was specified. And essentially, we've got an inverted U with a 1-metre toe into the London clay. And essentially, the London clay is, for the short term, impervious. So if the ground treatment was successful, it would essentially cut off the groundwater and stabilise the ground sufficient for us to undertake the excavation and spray. A first option that was considered during the early design phase was permeation grouting. Unfortunately, the past ground failures meant that the perception of risk was too high, and that was quickly discounted. Another option that we considered was horizontal in-tunnel jet grouting, and you can see here there's a sketch of an enlargement every so often, followed by the installation of 300mm diameter freeze pipe boreholes. However, the problem with this was that it didn't decouple the tunnelling from the ground treatment works, so we'd essentially have to treat ahead of the face, stop tunnelling, and also verify the ground ahead of us before we were allowed to proceed tunnelling. So it was perceived as inefficient, really. The other problems with ground freezing technically were the variable water table at Victoria. We have dry conditions above the shoulder level, as you saw earlier on, and wet conditions below, so the ground freezing wouldn't be uniform throughout, and there was a perceived risk of freeze-thaw effects and movement, as well as heave associated with that solution. So discounting those two, the solution that was chosen was subvertical and vertical jet grouting, so all to be undertaken from the surface. Again, the reason for selection for vertical jet grouting and not horizontal jet grouting from the face was to decouple the activities. So the ground treatment could happen well in advance of the tunnelling. We could assure that the ground treatment was successful and then proceed to tunnel. You can see the pictures up above, a string of drills undertaken from the surface and single jet grout entities created into the ground. The perceived benefits of this were there was a low risk of grounding ingress from a single defective column. It also stabilised the sand and created that impermeable bathtub that we saw earlier on. And it also stabilised the ground with sufficient stiffness to reduce volume losses that were predicted at 0.5% prior to the start of the tunnelling works. Here's a little animation of the jet grouting process. You can see the geology on the right. The first challenge was to undertake sleeves past the surfaces. So we saw earlier the extreme density at the surface at Victoria. No doubt multiple services in the vicinity. To avoid risk of hitting any of those services, the first task of the enabling works team was to identify the location and insert sleeves that would then allow the operators to safely drill past the surfaces. Following that, we installed a spoil return duct. The idea behind installing the spoil return duct, and this is the first time it was ever undertaken on a project for jet grouting, was that it would allow a path for the jet grouting to, a known path to return the spoil rather than the spoil to disperse and find its way into unknown or existing structures. Following this, we drilled down to the required depth into the London clay with a 1 metre embedment to form the cutoff. We pre-cut the clay twice. The reason for the pre-cut was blockages in spoil return could lead to overpressurization of the return duct and thereby causing settlement for the underlying tunnels below and heave on the surface above. So we used a lower pressure to pre-cut the clay twice to soften the clay. Following that, we would pre-cut the sands and gravels, pre-cut the alluvium, undertake the jet grout column, and that would form the ground treatment. So how did that work out? Here's a 3D model showing some of the complexities of the work in grey. We've got the existing assets. So we've got where I'm running my mouse pointer now. We've got the Victoria line, northbound and southbound running tunnels. And up here, running across the screen, we've got the district and circle line. In red and purple, we've got the NATM or SCL VSU tunnels. And you can see the services that were identified in a 3D model on the surface. Following this, we were able to lay out each and every jet grout column on the project prior to commencement of the works. Some 2,200 columns were installed to enable the tanking and jet grouting to be successful in cutting off the water. Here are some pictures during the enabling works. Here we have the team identifying, locating services and installing these spoil return sleeves and ducts, which I'm hovering over now. You can see that these sleeves were then safely inserted past all the services, surveyed and identified, so the drill operators could drill through these with confidence and without risk of striking any of the utilities. You can see here the bus terminus, etc. So local diversions being undertaken to install the sleeves, series of sleeves being installed, and the ground being backfilled ready for the jetting operation. Some pictures during the works of local work sites. So you can see the bus terminus and the buildings remaining operational, so keeping Victoria moving, and locally working in constrained work sites with the jet grouting rigs to install the 2,200 columns prior to the tunnelling works. In some cases, where we're passing beneath buildings, it was not possible to undertake the works from the surface. So the groundwork subcontractor Keller developed special restricted headroom rigs, and you can see them here working in a basement, pre-boring and installing the jet grout sleeves for tunnelling in the future. Here we're working next to listed buildings, so we were able to knock out the buildings, support the listed facades, lower machines, jet grouting rigs into the buildings and into the space created in the buildings, undertake the jet grouting, and then reinstate the buildings. So having done all that, one of the major challenges was then to assure that the ground treatment was successful. So the reason for selecting jet grout, as I said earlier, was to decouple the two activities to allow us to undertake some verification prior to the tunnelling works. To do this, we used BIM modelling to mitigate the geotechnical risks. So I'll go into that now. To do that, the first operation was to set out the jet grout columns and undertake a series of trials. So you can see a schematic here of various jet grout columns that are laid out next to the existing platform tunnels. Oops, let's go one back, sorry. Existing platform tunnels, which I'm hovering over now. And what we did there was we undertook a series of 10 columns to verify the various parameters. So here you can see measurements of design diameter versus measured diameter, and these are measured using physical calipers. We use indirect hydrophones and also retrieving cores from the jet grout trials and undertaking lab and field tests on those to verify the parameters. What we found was the actual diameter was within plus or minus 20% of the specified diameter. The next idea of the jet grout trials was to look at the effects that the jetting operation would have on existing adjacent underground structures. So we obviously had the district and circle line brick structure. So we jetted within 40 centimetres of a brick structure, as you can see on the left here, and it just showed some scouring of the brickworks, but nothing detrimental. On the right, we undertook a mock-up of jetting next to cast iron within 60 centimetres, so 2 feet. And that was to simulate jetting next to the existing Victoria Line northbound and southbound cast iron platform tunnels. Some slides of core recovery from the jetting operation. So we were able to undertake uniaxial compressive strength and elastic modulus testing on these. On the left, you can see an example of a good core. On the right, you can see the example of a core where we've got sand pockets. So using these sort of intrusive surveys, we were able to refine the jetting parameters and tweak them as we needed to ensure that when the operation was undertaken on site, everything would go as planned, with hope. So having done all that, the first structure of the works was a shaft. And to verify the jet grout columns in situ, we undertook a series of columns inside the shaft, which you can see here. You can see 1, 2, 3 jet grout columns in between the excavator. So having exposed these, this allowed us to physically measure and observe what the columns look like in situ before we undertook any of the tunnelling works or got below the water table. Another aspect of assurance and creation of the BIM model was adequate data capture during the work. So we had 2,200 columns that were jetted. These were laid out in a CAD BIM software, which then reported the outputs directly into a spreadsheet, which was fed into the total stations and the onboard computer systems on the jet grout rigs. This allowed the operators to set them out autonomously and accurately. And the as-built data was then also collected for production of an as-built jet grout model. So you can see here on the left, this is the design model. On the right, we've got the as-surveyed model the as-surveyed information collected from the site crew. So this allowed us to compare the design versus the actual location and diameters of jetted columns. Having done so, we were able to create the BIM model to undertake risk reviews. So you can see here we've got a series of columns from the data collected from the onboard computer systems, and we were able to colour the columns in various colours, identifying various levels of risk. So we've got white columns which are yet to be jetted, the green columns which have been jetted as per the design, red columns are non-conforming columns, and purple columns were columns that had been reviewed and accepted as conforming. And we were able to do this for each and every single entity of columns, so 2,200 times, but do it all electronically and use this as a risk assurance mechanism. So what we were able to do to verify the as-built ground treatment was produce a negative model. So rather than realise where the columns are, is to realise where the columns aren't. So on the left, we have the as-built model of the columns, and on the right, we have the model of the design model of the tunnel. And you can see here that once we add those two together, we get these little, and add the geology onto the information here as well. as well as advanced sequence. You can see on the top right, so each one of these colours is an advance. What we're left with is an annulus or a gap model. So each one of these little orange pockets that you can see on the top left represents a gap in the jet grouting. This animation here basically shows step by step, as we advanced, we were able to identify each and every gap and see what risk they would pose. So you can see on the bottom left here, a substantial gap opening up at clay level or just above clay level. So prior to any tunnelling works being undertaken, we had a 3D visualization of geotechnical risks and risk per advance. And as a team, we were able to sit and undertake risk assessments and propose mitigation or contingency measures as necessary. What we found was we would use a traffic light system for risk assessment of the gaps. You can see here on the left where I'm hovering my mouse now, a substantial gap at the low interface layer between the clay and the gravels. This gap, if not identified, would have caused major inrush into the tunnels. However, it was identified. So we came up with a series of mitigations. If we had an enclosed gap within the excavated volume, we would essentially drain it and continue mining, which is a low risk, considered low risk. If we had small gaps which were cut off from the groundwater, we would potentially treat these on a case-by-case basis, again, still considered relatively low risk. However, gaps in the crown above the shoulder levels were considered high risk. But if they were above groundwater level, they were considered a lower risk. Gaps, obviously, in the crown above, in the sands and gravels in the groundwater level, were likely to be unstable. You can see an example of one here on the top right where I'm hovering my mouse now. So a substantially sized gap coming into the daylighting into the tunnel within the water table, and these needed some action prior to tunnelling. So having built the jet grout model, we used the existing 3D model of the existing structures, tied those together, surface buildings, proposed SCL or NATM tunnels, geology, ground treatment, the gap model, and before we started any of the tunnelling works, we were able to identify across the project areas that needed treatment. So you can see in some areas some substantial gaps. There's one where I'm hovering, another one where I'm hovering now, another gap right at the start of the tunnelling works, which proceeded from this shaft, and a significant further gap here and around the shaft. So there was still plenty to manage prior to the start of tunnelling that we would have to manage during the tunnelling works because the jet grouting could physically not be undertaken from the surface. You can see here another snapshot of the gap model. Here now we've added the advanced sequence for various tunnels step by step, leading up to these gaps next to live adjacent structures. So we'll move on to see how we manage these gaps during the tunnelling. One of the key controlling mechanisms was the DRM and the RES process. In the UK, at least, the DRM stands for the Daily Review Meeting, and the RES is the Required Excavation and Support Sheet. So prior to the start of the day's tunnelling, the SCL engineer and the production team sit together and identify any hazards and any mitigation measures that would need to be implemented each and every advance for the next 24 hours. So having built the jet grout model, what we were able to do is set up a traffic light system per advance. So you can see up here for each gap identified on the top, whether we were in a green, amber or red, which is a low, medium or high risk gap. And we were able to supply the production engineers on the face and the miners with snapshots of what to expect in the face during tunnelling. So you can see here, for example, this is a theoretical face log on the left from the jet grout model. We can see the tunnel advancing. In the next advance, we expected 3 relatively large gaps, 1, 2, and 3, where my mouse is. So this theoretical face log was given to the production team at the DRM to know what to expect. On the right here, you can see the shift engineer's log on what he encountered on site. And here we have a picture comparing the two of what was encountered on site. So on the right, we have the jet grout in light grey and the untreated pockets in 3 distinct areas. So as tunnelling work started, we were exposing untreated ground, but they were matching very well with the theoretical gap model. So this gave us a lot of assurance that essentially we were aware of upcoming risks and gaps, and we would be able to successfully treat those to avoid any hazards during the tunnelling. In terms of dealing with the gaps, once we had identified the gaps, we had various types of gaps and contingency measures put in place for them. This one, for example, is dealing with a known gap. And what we have here is we have a known gap coming up ahead of the face, and this potentially is a high-risk gap that contains water. You can see a picture of it on the right. So what we're doing here is we're drilling TAM pipes and lances into the face from a sealed face, which is stable, a sufficient distance away from the face. You can see in the picture we've got untreated gravels and water returning. Following the drilling and identification of the gap, the production team had in place procedures for dealing with these events, and we would essentially set in place a series of tasks identified for each gap. And here, from memory on this gap, it was just grout injection ahead of the tunnel using local permeation grouts, so sodium silicate grouts, to cut off the water and stabilise the gaps. Here's another example, which is a significant gap from the face. So having identified the gap, we stopped in this instance approximately 5.5 metres short, sealed up the face. You can see on the top the face is nice and stable, nice and dry. Drilling TAMs into the face in the top right, returning, identifying untreated ground and water, and then undertaking treatment from a stable environment and verifying that treatment before continuing to advance. A couple of little bullet points down the bottom which are quite interesting were what we did note is when we drilled into gaps, if we drilled into a gap and the water that it returned was warm, that meant that it was confined. The reason for this we identified was that as the jet grout, which is cementitious hydrated, it heated up, the trapped water remained heated with it. So when we drained into it, it released warm water. So we were confident then, having felt warm water return, that there was no water path to the outside aquifer. However, if it returned cold water, this confirmed that the gap was connected to the outside aquifer and thus possessed a high risk of instability. And so a series of events would be actioned as per the agreed measures. The good thing about this and having pre-prepared plans was that plans could be actioned at the face by the shift engineers without need for consultation with the senior SCL engineer or senior production team at any time. It was essentially a methodical process. Here's another example of a high risk area that we tunneled through. You can see a theoretical face log. So we've got the tunnel top heading and bench advance, the London clay level shown here, the water table at shoulder level. We can see this is a high risk area with lots of gaps predicted in the annulus and also in the face. Again, we were able to action these, drill into the gaps, identify the connections, and undertake the appropriate measures. And here's a picture showing theoretical versus actual. If I just rock and roll back and forward here, you can see that in the tunnel face we can only see one gap. However, there are a large number of gaps connected to the outside in the annulus which we can't see, which we had pre-treated. So going forward again, having identified the gap in the face, we were again confident that we would identify the gaps in the annulus as per the models. So drill vectors, etc., were set out and a series of remediation set in place prior to advancing the tunnel. Here I had another video, so I'll just quickly go off screen here for a moment and see if I can show you. Sorry about the So I'll just pause there for a minute and come back to that. This is essentially the gap which I showed you earlier on with the three distinct zones. It's hard to see on here, but you can see the large sand pockets. And if you watch the wheel as it turns, you'll see how quickly it mucks out the sand or untreated areas and the difference between the strength and the jet ground. So there we are. That was an example of a large untreated pocket. Even though the gaps were quite large in that area, having known that they were coming and that they were dry, we were happy enough to muck out the ground, and also the mining gang were sufficiently confident that the ground ahead would be stable. Not everything always went to plan. So here we had an unknown gap, and this is a potentially defective column. So this is during a top-heading advance of a large escalator tunnel. This wasn't expected, and here we had a large void in the left of the annulus, down at below water level. And you can see here, this is on the bottom where my mouse is now. This is the top heading of the escalator tunnel, right above the platform tunnels. We're only talking about potentially 10 feet, if that. And what we found is that this column that was circled was defective. However, there was no inrush, and the reason for this was the design. So we had a double cutoff system. So you can see here, now highlighted in green, we always had a second column as a cutoff to the water table in case of one defective column. So as opposed to the right, you can see here we've always got two columns between the extrados of the tunnel and the outside world. So in the event of an unknown defective gap, the redundant column on the outside would hopefully, and did very successfully actually, mitigate against ground ingress. Here on the right you can see the gap now filled with shotcrete, successfully sprayed up, additional measures, drain pipes, etc. installed, and mining continued. So that was one of the risks, or one of the biggest challenges, was the geotechnical challenge. The next biggest challenge was operating next to the operational station. So undertaking all this next to the live platform tunnels of the Victoria Line, District and Circle Line. So development during the VSU design phase, the early design phase, was a propolis connection into the existing station to minimise impacts of the adjacent tunnelling works. So you can see here we've got the existing tunnels in grey once again, and the proposed VSU tunnels intertwining in between the existing assets. And in certain areas where we've circled, we've got connections into the live platform tunnels. This is an excavation sequence showing that escalator again. Again, the one we saw just a second ago that had a gap in the top. So we needed to build this 9.5 metre diameter tunnel diving into the existing platform tunnels. These are the existing structures. So we had a series of platform tunnels left and right, north and southbound. A concourse tunnel, the bit in orange, was decommissioned. Everything else remained in service. These two cross passages were decommissioned, and we had to demolish these on the way down. Again, the geotechnical conditions operating very close to the surface buildings underneath the water table as usual. So the first, to make this sequence successful, one of the first steps was the enabling work. So what we had to do was decommission part of the concourse tunnel and backfill the existing tunnel to form a ramp for the SCL to bear on as we came down. So the part in red was decommissioned. Following this, we drove the upper machine chamber. Out of the machine chamber, we drove it from pilot heading to drop down into the station, so we didn't have to use the station itself for access. We could access all from the non-operational side. We filled the internal cross passage and concourse tunnel with concrete, with foam concrete. That allowed mining to continue. Here you can see a cross-section and a diagram through the proposal. Following this, once we had access into the operational level from outside, we were able to construct these two cross passages either side to stiffen up the platform tunnels. Here you can see we've got this is the concourse side where I'm pointing to now. We were able to drive a small pilot heading, install the strongback to the back of the platform tunnel, which I'm pointing to now. So this remained operational. Where this gentleman stood is up here at this level, ready to install the strongback, followed by strongback installation. Following this, we were able to sequentially mine down. So you can see here we're mining down at where my mouse is now, installing props to the platform tunnel in 2 benches, and then finally a third bench to install the strongback down to the base. And here you can see we've reached the final formation level. There's the bottom strongback, which is this member shown on the drawing. And you can see that's me standing there looking very pleased. And where my mouse is hovering now, that's the live station platform on the other side. So we've still got trains operating there every 2 minutes in peak hour. Following successful construction of the propless connection, we had to backfill the temporary works to allow us to complete the SCL drive down into the operational station. And essentially what we formed is something that looks like this. This is another example of a propless option for a smaller tunnel coming into the escalator barrel. Here we were able to drive SCL headings up to the back of the platforms in small advances, stiffen them up with jam frames, as you can see on the right here, and cross members from the back, and then complete the works. So the only time we had to encroach into the existing station was during engineering hours, and it was just these 2 men one night installing bolts over the length while the station is closed. That's an example of the completed section. So the platforms remained live throughout the works. All the SCL tunnelling is undertaken from the non-operational side, and any impact is minimal. And that was essentially a summary of the challenging technical aspects of the SCL tunnelling. So just to run you through the progress to date, the tunnelling is now complete at Victoria Station Upgrade. We didn't have any incidents geotechnically or tunnelling wise. You can see here all these tunnels now in orange have been successfully built. We've got a new ticket hall in green, which has been completed. The escalator barrel is now connected and the escalators have been dropped in. These passenger adits and an underpass below the district and circle line has also been completed, as of all the other works. The north part on this side is due to open later this year. Here's some pictures of the SCL on completion of the works. This is looking south, and if you look, the water level is approximately where my mouse is. However, the tunnels remain relatively dry, and that's a testament to the success of the jet grouting works and in-tunnel mitigation measures during the drives. Secondary linings are now completed. At Victoria, we've got a sheet membrane and cast in situ steel fibre reinforced secondary linings. Most of the tunnels are being lined as we speak, also nearing completion. This is an underpass below the district and circle line. This is actually an old photo, but quite an impressive photo. This work's now complete. It's not really that clear here, but where my mouse is hovering now is, sorry, I lie, where my mouse is hovering now is the level of the tracks of the district and circle line trains, and they were kept running at full capacity while we were mining beneath the live tracks. And finally, some pictures of our final breakthrough. And in summary, all that was accomplished in this congested environment, keeping Victoria moving. So we successfully completed the works without any onerous impacts on either the surface or the operational assets. And I think that's all for me. I hope you enjoyed that. And if there's any questions, feel free to ask.
Dr. Bedi, thank you so much for that wonderful presentation. We really enjoyed your graphics, too.
Thank you.
We'd like to invite the attendees to use the chat panel to submit any questions. We already have a few questions from today, so I'll go ahead and start reading those off. The first question: how did the jet grouting perform at the interface between the gravels and the London clay, considering the extremely different permeability of the materials?
If I can go back to my slides, it actually performed very well, and the reason for that was this pre-cutting that we spoke of. So you can obviously a valid point. The London clay and the Thames gravel are very different in terms of permeability. So what we had to do was adjust the parameters of the jetting for the London clay, so a higher pressure jet and 2 pre-cuts to soften the clay. And in the gravels, we only had 1 pre-cut and lower pressures to create the same diameter column. And again, all that was confirmed during the jet grout trials, where we tried various permutations of jet pressure and pre-cutting to achieve a uniform diameter throughout the different strata. So all in all, it worked very well. Unfortunately, except that one location, which I showed you earlier on, where we had quite a big hole from a missing column. Let's see if I can go back to my slide that brought that one up. And here we are. And that did happen right at the interface of the London clay and the river terrace deposits. The reason for that we identified later was an incorrect pre-cut overlap. So that column was actually constructed. There was a blockage during the London clay. The automated systems then depressurized the lines so we wouldn't heave the ground or cause any adverse effects. When we came back to redo that column, unfortunately the pre-cut wasn't undertaken again, so the column was attempted to, it was essentially recontinued from where it was let off rather than pre-cutting and restarting again. But otherwise, that one incident, everything else was quite uniform. The jet grout columns themselves were quite uniform throughout the various strata.
Great, thank you. The next question reads: the ground improvement measures were quite extensive on this project. Approximately what percentage of the overall project costs were associated with the ground improvement and jet grouting?
In estimate, between 10 and 15% of the project costs was the jet grouting. However, the jet grouting was a substantial element of the works. Essentially, 2,200 columns in the ground, and again, the consequences of not achieving a successful ground treatment speak for themselves, really, from the earlier video showing the ground conditions. So I think we as a team feel, and the client, if I can speak for the client, also feel that it was a great success and actually good value for money.
Excellent. The final question we have reads: you said they predicted a 0.5% face loss upon completion of jet grouting. Was the face loss monitored during excavation, and if so, how did it compare to the predicted value?
Yes, indeed, it was. We had ground sediment monitoring and in-tunnel deformation monitoring during the works, and at the risk of showing off, it was 0.48% back calculated at the end of the works.
Great, thank you so much. That's all the questions that we have for today. We'd like to ask our attendees, if you have any further questions, to please reach out to Dr. Bedi at the information on the screen. And we hope that you can join us for next month's UCA Young Members webinar. We would host that on July 27th, although we haven't confirmed our speaker just yet. Dr. Bedi, do you have any closing statements you'd like to make?
No, thank you very much for all those that attended, and I hope you enjoyed it. And thanks again.
Of course, thank you so much for presenting. We really enjoyed the session.